Welcome back to Calculus 2. I'm Dr. Jeff Groh. There are a few loose ends to tie up. We're going to talk about logs and exponential functions. This textbook that you are using is subtitled Early Transcendentals. The transcendental functions are your natural logs and exponential functions, say e to the power x. We mentioned in Calculus 1 that we were not then able to develop the theory of logs and exponential functions properly, and that we would have to wait until Calculus 2 to do it right. It's that time. We're going to make the following definition. The natural log of x is, because I said so, this is a definition. Definitions you accept, theorems you prove. The integral from 1 to x of 1 over t dt. Note that this is defined provided x is bigger than 0. However, if x is bigger than 1, because 1 over t looks like this, if we're integrating from 1 to x and x is bigger than 1, you'll get a positive value. If you integrate from 1 to x where x is less than 1, you'll get a negative value for the log function. The domain is from 0 to infinity. At t equals 0, the function 1 over t suffers a discontinuity. And as far as we're concerned right now, you can't extend that below x equals 0 then. There are some elementary facts that we can pick up pretty quickly about this function. First, I want you to recall the fundamental theorem of calculus number 1. That says if you take the derivative of the integral from a to x, no matter what a is, of f of t dt, you get f of x. You plug that x right into that function, whatever it happens to be. We can see right away, I'll write this down as a little lemma, that the derivative of the natural log function, it's the derivative of the integral. You plug the x in. It's 1 over x. Also, if x is greater than 0, then the derivative of ln of x is greater than 0. If the slope of a function is positive, that means the function is increasing. Thus, ln of x is monotone increasing. In fact, it is strictly monotone increasing. It will strictly increase. Note also that because the derivative exists on the interval as x goes from 0 to infinity, it follows that the natural log function is continuous. So I'll write, note that ln of x is continuous on the interval 0 to infinity. Just because we've called something the natural log doesn't mean it has all of the properties that we expect it to have. We have to demonstrate that it does. So first, we'll show that the log of xy is the log of x plus the log of y. Also, the log of x to the power r is r times the log of x. And then the log of x divided by y is the log of x minus the log of y. Your basic properties of logarithms. On part A, we'll begin with the log of xy. That is, by definition, the integral from 1 to xy of 1 over t dt. By a property of integrals, we can break this integral into pieces. The integral from 1 to x, 1 over t dt, plus the integral from x to xy, 1 over t dt. The first part is the natural log of x. We need to prove that the second part is the natural log of y. And to do that, we'll make a substitution. We'll set u to be t divided by x. Then du will be 1 over x dt. We take the derivative with respect to the variable t. You can see then that we get the natural log of x plus the integral. Now if t is equal to x, u is 1. And if t is equal to xy, u is y. T is going to be replaced by x times u, and then dt gets replaced by x du. The x's cancel out, and we're left with what is, by definition, the natural log of y. We have the natural log of x plus the natural log of y, which is what we were trying to show. We next look at the natural log of x to the power r for some real number r. This will be, by definition, the integral from 1 to x to the power of r, 1 over t dt. It's at this point that we set u to the power of r equal to t, so that r u to the r minus 1 du equals dt. Let's see what we get. If t is equal to 1, u is 1 as well. If t is equal to x to the power of r, then x to the power of r equals u to the power of r, u is equal to x. T is u to the power of r, but dt is r, u to the r minus 1 du. This r can come out. What's left over after we cancel r minus 1 factors of u is r times the integral from 1 to x of 1 over u du, and that is exactly r times the natural log of x. For part C, it's easier. Suppose we have the log of a over b. That is the log of a times b to the minus 1. By part A, we can write this as log of a plus the log of b to the minus 1. And by part B, we can write that as log of a minus log of b. And that's it. What is the base of the natural log of x? Let's look at the derivative of the natural log of x evaluated at x equals 1. That is the derivative of the integral from 1 to x, 1 over t dt, evaluated at x equals 1. How do we do that? We're going to resort to the definition of the derivative. This will be the limit as h goes to 0 of the integral from 1 to 1 plus h, 1 over t dt, minus the integral from 1 to 1, 1 over t dt, all over h. We're evaluating this at 1 plus h and then at 1. This second integral is, of course, 0. This leaves us with the limit as h goes to 0 of 1 over h, the integral from 1 to 1 plus h, 1 over t dt. This gives us the limit as h goes to 0, 1 over h times the natural log of 1 plus h, But by the properties of logs, we can bring the 1 over h up as an exponent here inside of the log function. The log is a continuous function, and limits pass through logs, so we get the limit on the interior as h goes to 0 of 1 plus h to the power of 1 over h. Also, by a different path, if you take a look at the derivative of that integral from 1 to x, 1 over t dt, evaluated at x equals 1 by the fundamental theorem of calculus, we have 1 over x evaluated at x equals 1, and that is 1. Remember that if you have log base b of b, you get 1. And since the logarithms are monotone, there's only one place where you can get 1, that's at the base. That means whatever this limit is, that's the base of the natural log. We'll make the following definition, that base is called e, and it is, by definition, the limit as h goes to 0 of 1 plus h to the 1 over h. Whatever that limit is, it's some number, that is the base of the natural log. Since the natural log is strictly monotone increasing, it has an inverse defined across its entire domain. Inverse functions are denoted by a superscript with -1. So if we set f of x equals the natural log of x, f inverse of x will be, by definition, because we said so, capital XP of x. Notice we're not assuming that this is equal to the base e to the power of x. That's something we're going to prove. We know that the domain of the natural log is 0 to infinity. It's not too hard to show that its range is everything from -infinity to infinity, which means that the domain of exp will be -infinity to infinity, and the range will be 0 to infinity. It will only output positive values. Also, by the definition of inverse functions, we have the following two relations. The inverse function of the function, they cancel out. Also, the natural log of x is x. Whatever the function does, the inverse function undoes, and vice versa. We need to prove certain properties of this function that we've just defined. In particular, we will show that when you exponentiate a plus b, you get the same thing if you exponentiate a times exp of b. Here's how we prove this. We'll set a to be the natural log of some value x and b to be the natural log of some value y. This is legitimate to do because for any real number a you plug into exp, it outputs something that's positive, and that will go into the domain of the log function. Same thing for b. Then we have exp a plus b is exp of the natural log of x plus the natural log of y. But by the property of logs, we get exp of the natural log of x times y. But now exp and log cancel out, and that gives us x times y. But if we solve these for x and y, we'll get exp of a times exp of b, and that's the end of the proof. We'd also like to show that the derivative of exp of x is exp of x. Kind of this is one of those basic properties that you learned way back in Calculus 1 that's true for e to the power of x. We don't know that exp is e to the power of x yet, but we will prove that it satisfies this common property. This property we did not fully justify in Calculus 1. We can fully justify it here. What we'll do is we'll start by setting y to be exp of x. If you take the natural log on both sides, on the left side you get natural log of y. On the right side you get the natural log of exp of x, and since log and exp are inverse functions, they cancel out. Thus, when we take the derivative, we'll have 1 over y dy dx, we're searching for dy dx, equals 1. And that implies dy dx, the derivative of x, is y, and that is exp of x, ending the proof. It follows as an immediate corollary that the integral of exp of x dx is exp of x plus c. We will now show that this exp function, so mysterious, is in fact the number e to the power of x. First, the natural log of exp of x is x because these are, by definition, inverse functions. In addition, ln of e to the x is, first, by property of logs, x ln of e, and we already know the natural log of e is 1, so we just end up with x. So we know natural log of exp is natural log of e to the x. These two equal each other. It follows, because the natural log is a one-to-one function, it's strictly monotone increasing, that if the natural log of a equals the natural log of b, then in fact a has to be equal to b. So we deduce then that exp of x is e to the power of x. That finishes our theoretical development of natural log and exponential functions, but we have some other applications and some extensions that we can make. Let's do an example real quick. Suppose we're integrating e to the x over 3 plus e to the x. This is in the form the integral of f prime over f. Those are, in all cases, the natural log of the absolute value of f plus c. We deduce then that the answer here is the natural log of the absolute value of 3 plus e to the x plus c. In this case, because 3 plus e to the x can never be 0, the absolute values are superfluous and may be exchanged for parentheses. We often use other bases besides the natural base. First of all, the derivative of log base b of x is 1 over the natural log of the base times x side of the log. Also, the derivative of b to the power of x, some base, is equal to the natural log of that base times the function b to the power of x. We prove this by reducing to known. Suppose we start with y equals b to the power of x. If we take the natural log of both sides, on the right-hand side, the x will come down by one of the properties of logs. Using implicit differentiation, we'll have 1 over y prime equals 1 times the natural log of b, since b is constant. We'll move the y over and get y prime, which is the derivative of b to the power of x, is the natural log of b times y, which is b to the power of x. Now, if y is equal to log base b of x, that implies that b to the power of y is equal to x, taking b to the power of both sides of the above equation. Using the theorem we just proved, taking the derivative on both sides, we'll get log of b times b to the y, and then by the chain rule times y prime, that's implicit differentiation for you, is equal to 1. We'll solve for y prime, but remember, b to the y is x. And that gives us y prime, which is the derivative of log base b of x, is 1 over the natural log of b times x. It follows as an immediate corollary that when we integrate b to the power of x, we will get b to the x, but divided by the natural log of b plus a constant of integration. You can see that because if you take the derivative of the right-hand side, the c will go away. We'll get an extra factor of log of b, which will cancel the log of b in the denominator, leaving the integrand b to the power of x. So for example, suppose you're integrating x 2 to the x squared dx. What do? You kind of see the derivative of something more or less lying around. So it looks like a u substitution is required first. U is x squared, so du is 2x dx. We have the x dx, but we don't have the 2, so we'll divide the 2 off. We'll put that 1/2 out front and have integral of 2 to the power of u du. Well, what is the integral of 2 to the power of u? It's 2 to the power of u. We'll have the 1/2 in the denominator, but we'll also have a natural log of 2 in the denominator plus c. We're almost done. The only thing we have to do is substitute in for u. We'll have 2 to the power of x squared divided by 2 natural log of 2 plus c. In our next example, suppose we're integrating 7 to the power of square root x over the square root of x dx. It looks like a substitution again. If u is the square root of x, then du, what is the derivative of the square root of x? I want you to memorize what the derivative of the square root of x is. It's 1 over 2 root x. And then if you have an infinitesimal on one side, you have to have an infinitesimal on the other to balance it out. We don't have this 2, so I'm going to put that on the other side. We'll have 2, the integral of 7 to the power of u du, which we know is 2, 7 to the u, divided by the natural log of 7 plus c, and that's 2 times 7 to the power of the square root of x, divided by the natural log of 7 plus c. We're now able to prove the power rule for derivatives. And our proof will be accurate. The power rule says if you take the derivative of x to the power of some real number r, you get r times x to the r minus 1. Let's prove this now. We'll set y to be x to the power of r. Then what is the natural log of y? Well, it's the natural log of x to the power of r, but r can come out by the property of logs. If we now implicitly differentiate each side, we'll have 1 over y times y prime is r divided by x. We'll move the y back to the other side and get y prime, y being x to the power of r, y prime is the derivative of x to the power of r. And remember that y is x to the power of r, and x to the power of r divided by x is x to the power of r minus 1, and that's it. We're next going to look at exponential models. There's something called the natural growth law. A population P satisfies natural growth if the rate of growth of the population is proportional to the population size, if the population satisfies this differential equation. Let's also suppose an initial condition that the population at time 0 is some value, P naught. A differential equation together with a piece of data like this gives you what is called an initial value problem. When you solve a differential equation, you have to undo a derivative. You should get a constant of integration, meaning that you should have a family of curves that satisfies the differential equation for different values of the constant c. Stating a specific point that the curve passes through picks out one among that family of curves that satisfies the initial data. Natural growth is sometimes called Malthusian growth, after Malthus, who I think in 1776 declared, "We're all going to die." Why are we going to die? Because, according to this model, you get exponential population growth. He believed that if the human population grew above 1 billion people, then there wasn't enough arable land to feed all those people, so we'd all starve to death. No, Malthus was wrong, clearly, for a number of reasons, but he had mathematical justification to back up what he was saying. It was scientific. So throughout the years, there are always going to be scientists who say, "You're going to die." Don't believe one of them. Here's what we have to do. Let's separate this and integrate. We'll put the p over here and the dt over there, and we'll integrate. We'll get the log of the absolute value of p plus a constant equals kt plus a constant. Notice I'm taking the constant on the left and combining it with the arbitrary constant on the right. The difference of two arbitrary constants is an arbitrary constant. Exponentiating both sides, we have the absolute value of p is e to the kt times e to the c. Notice that exponential functions don't output negative values. This will be a positive arbitrary constant. But the solution to an absolute value equation is x equals plus or minus a, which means p is going to be plus or minus some arbitrary positive constant. Well, plus or minus an arbitrary positive constant is an arbitrary constant. Let's just call this c, e to the kt. Through an abusive notation, we'll call it c. It isn't really the same c as over here, but they're both arbitrary constants, so let's just agree to call it c between friends. It's at this point that we use our initial data. P of 0 is some number p naught, where p naught is the size of the population at time t equals 0. We'll get p naught equals c e to the 0. Well, what's e to the 0? 1. And so the right-hand side is c. This arbitrary constant is the initial population size. You get p equals p naught e to the kt. So Malthus was right if all things otherwise ignored, all other factors ignored. We just look at the solution to the Malthusian growth law, we end up with exponential growth. Was it reasonable to assume that the rate of population growth is proportional to population size? Well, it depends. Think about it this way. If you lock 1,000 people into a building and keep them there for 10 years, giving them everything they need to survive, are you going to have 1,000 people in that building at the end of 10 years? It depends upon how well they like each other, right? You might have more. Now, let's suppose you take 10 million people and lock them into a big city and keep them there for 10 years and give them everything they need to survive. Are you going to have 10 million people in the city at the end of 10 years? And again, looks like you'll probably have more. But you'll probably have proportionally more than you would by locking the 1,000 people into a building. The rate of population growth is proportional to how big that population is. That's a reasonable assumption under many scenarios, but by no means the only possibility. There's something called doubling time. That's how long it takes for a population to double in size. We'll call that t sub 2. That'll be our notation for the doubling time. Whatever that is, twice p naught is p naught e to the power of k times the doubling time. When you plug t equals the t2 in, the doubling time, for your exponential function, you should end up with twice what you started with. Notice that p naught cancels out. The doubling time will not depend upon the initial size of the population. And what is more, we can solve for t2. We'll now take the natural log on both sides. The natural log of e to the power is just the power. It follows then that the doubling time is the natural log of 2 divided by the growth constant k. The growth constant will depend upon the nature of the particular population that you're studying. So for example, suppose I have an initial population of 1,000 bacteria in my smelly old shoe, my gym shoe, and that at t equals 1/4 hour, the population is 1,025. I want to find the doubling time. How do we do that? Well, the data that we're given allows us to figure out the growth constant. How do we do that? At t equals 1/4 hour, we have 1,025 population when we started with 1,000. We'll just solve this equation for k, the growth constant. We'll divide both sides by 1,000 first. When solving for something, remember this. You have to whittle away at the things surrounding it, starting with the things that are furthest away by the order of operations agreement. We have to get rid of the 1,000 first, because it's furthest from k by the order of operations agreement. This just moves the decimal place to here. Now we have to get rid of the e. We do that by taking the natural log of both sides. The natural log of 1.025, the natural log annihilates the exponential function, leaving you with 1/4 k. It follows then that k is 4 times the natural log of 1.025. From this, we can figure out the doubling time. t2 is the natural log of 2 divided by k, which is 4 times the natural log of 1.025. Well, how much is that? My calculator is giving me about 7.01, let's say 7.0 hours. That smelly old shoe will be twice as smelly in 7 hours. There's also something called half-life. That's how long it takes to have half the population if the population is decaying. It's decaying when the rate of growth of population is negatively proportional to the population size. It is always good form in physical models for your constants to be non-negative, for them to be positive. So if it is negative, put a negative out front and make it into a positive value. In this case, the bigger the population, the faster it's shrinking. This is a model for exponential decay. And we'll have p equals p naught e to the minus kt by the exact same analysis as before. So how long is the half-life? We'll denote the half-life by t1/2. we'll have 1/2 p naught equals p naught e to the minus k at time t 1/2. Notice that the initial population size doesn't matter at all. We'll take the natural log on both sides. But keep in mind, the natural log of 1/2 is the natural log of 2 to the negative 1/2, or negative natural log of 2. On the right-hand side, the log annihilates the exponential function, leaving negative k times t 1/2. The negatives go away, and t 1/2 is, surprise, surprise, natural log of 2 divided by k, the exact same formula as for the doubling time. The only difference is we have a minus here and a minus here. We don't get a minus here. This is positive. Let's look at an example using carbon-14. Carbon-14 is made in the atmosphere when nitrogen molecules are bombarded by radiation from outer space, converting it to an isotope of carbon, carbon-14. Carbon-14 is radioactive. You just leave it there, it's going to be gone in some period of some thousands of years. But that means that whatever carbon-14 is in the atmosphere now was not here when the Earth formed. It has been created over time. What is more, above-ground atomic tests have released a lot of carbon-14 into the atmosphere as well, and that means that for anything that has died since atomic testing, the carbon-14 dating methods are invalid. Only for things that died before above-ground atomic tests can you use this as a dating method. This has a half-life of 5,730 years. So after that period of time, you have only half as much of the carbon-14 as you started with. There's a well-known proportion of carbon-14 in the atmosphere, or at least there was before above-ground atomic tests. And living things incorporate that carbon-14 in their body just like they do regular carbon, because chemically it behaves just like carbon. But they can only continue to put that carbon-14 into their body while they're alive. Once they're dead, they have all the carbon exchange with the environment they're going to get. That carbon-14 in their bones it's going to decay away. So if a bone has 32% of the carbon-14 when the animal died, when did it die? First, we'll use this half-life to figure out the decay constant. 1/2 of whatever we start with is p naught e to the k times 5,730. The p naught can cancel off. What we need to figure out is the decay constant for carbon-14, and this should be minus. If we take the natural log on the left-hand side, we get the minus natural log of 2, just like before. And the natural log on the right-hand side is minus k times 5730, and hence k, the decay constant, is the natural log of 2 divided by the half-life. We have 32% of the amount of carbon-14 that we started with, so 0.32 p naught equals p naught e to the k times whatever the age of the object is. We now know what k is. Again, consider that p naught doesn't matter. And we have, of course, a minus right there. I keep forgetting that. We'll take the natural log on both sides. The natural log of 0.32 equals minus kt, and we know what k is. So we'll divide the negative k over and get t equals minus log of 0.32 divided by k. Now k is natural log of 2 divided by 5730. Moment of truth. How old is that bone? My calculator is telling me about 9,400 years. Finally, today, I'd like to talk about hyperbolic functions. You may have seen these before. We're going to make the following definitions. The hyperbolic sine of x is, because I said so, e to the x minus e to the minus x over 2. Just accept this. That is its definition. We'll explain why we call these hyperbolic functions later. A hyperbolic cosine, oh, by the way, this is pronounced sinh, and this is pronounced cosh. Cosh of x is, because I said so, e to the x plus e to the minus x over 2. Well, what about the others? Tanh. Can we just call this sinh over cosh and define all of the remaining hyperbolic trig functions by ratio identities like this? You know what to do. The basis for calling these hyperbolics is the following theorem. Cosh squared of x minus sinh squared of x is equal to 1. Not plus, minus. By the way, if these were the regular circular functions, cosine squared x minus sine squared x would be cosine of 2x by the double angle identity. But these are hyperbolic trig functions. They satisfy similar identities to the regular trig functions, but always a little off. We've got to prove this. Let's take that left-hand side and use the definitions. The only thing we have to go on right now. E to the x plus e to the minus x over 2, quantity squared, minus e to the x minus e to the minus x over 2, quantity squared. Both of these terms are going to have denominators of 4, so I'm going to put that 1/4 out front. And then we'll FOIL out the numerators. Remember that if you have a plus b quantity squared, you get a squared plus 2ab plus b squared. E to the x squared. You multiply the exponent and get e to the 2x. If I take the first times the last, I add the exponents. But if I add x and negative x, I get 0. I get e to the 0, which is 1, which I have to double. And then, when we square the last term, we get e to the minus 2x. For the next grouping, when we square the differences, we'll have a minus. So we get e to the 2x minus 2 plus e to the minus 2x. Now we combine like terms. E to the 2x's cancel, e to the minus 2x's cancel, and that leaves 2 minus negative 2, which is 4, times a fourth is 1, and that's the end of the theorem. As you may know, if you have a circle, x squared plus y squared equals r squared, you can parameterize it as x equals r cosine t, y equals r sine t. At different values of t, you'll be at different locations on the circle, and it will be swept out in a counterclockwise fashion. What if you have x squared minus y squared equals 1? That's no longer a circle, folks. That's a hyperbola. You can parameterize it. X equals cosh t, y equals sinh t. It will satisfy the appropriate identity, and that will give you a parameterization, but unfortunately, not the preferred parameterization, because this won't give you the whole hyperbola. A hyperbola will look something like this. Our parameterization will only give you the right part, and the left part, unfortunately, because cosh can't be negative. It's e to the x plus e to the minus x all over 2, so it won't give you the left half. There is another parameterization that'll work. X equals secant t, y equals tangent t. That will give you both sides. There are, of course, a number of other identities, but I only want to give you some of the more important ones. Let's look at the even-odd identities. First of all, do you remember what an even function is? f is even if f of negative x equals f of x. So just like f of x equals x squared, when you replace x by negative x, the negative gets squared away and you end up with what you started with. Such a function is called even. You can see the negative would go away if the exponent were 4 or 6 or 8 or any even number. F is odd if f of negative x is minus f of x. And you can see if the powers were odd, you would get a negative left over coming out front. Now, functions may be even, odd, or neither. Well, as a matter of fact, every function can be decomposed into two pieces. The first one is even, the second one is odd. One of those pieces might be 0, and if so, then it's purely odd or purely even. How do you decompose a function into an even and an odd part? Suppose the function f is given, and we'll set h to be, by definition, f of x plus f of minus x over 2. Then notice that h of minus x is f of minus x plus f of minus x, but you just get h of x back. It means h is even. If I set g of x to be f of x minus f of minus x over 2, then that's odd. When you replace x by minus x, you'd have to reverse the subtraction to get back to where you started. But when you reverse the subtraction, you get a minus sign. And that's the minus that would pull out. It follows, if you take a look at this, h of x plus g of x. If you add them together, we get 2 of those f of x's on top divided by 2. That's 1 f of x. And f of negative x and negative f of negative x will cancel out. So that's just it. So every function can be decomposed into an even part and an odd part. It follows then that since cosh of x is e to the x plus e to the minus x over 2, that cosh is the even part of the exponential function e to the power of x. And since sinh is e to the x minus e to the x over 2, that it is the odd part of e to the x. If we take the derivative of the hyperbolic sign, then you're taking the derivative of e to the x plus e to the minus x over 2. The derivative of e to the x is e to the x, but the derivative of e to the negative x is minus e to the negative x. And that's a sinh. Derivative of cosh is sinh, not minus sinh. Always a little bit off. Similarly, the derivative of sinh is cosh. No minuses in this case. What is the derivative of tanh? Well, we can express this as a quotient, the derivative of sinh over cosh. Remember the quotient rule. Derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. The derivative of the top is cosh, but we're multiplying by the bottom, minus the top times the derivative of the bottom over the bottom squared. Don't be trying to cancel off of terms. You may not cancel terms in a fraction. You may only cancel common factors. What's the difference between a term and a factor? Terms are separated by plus or minus. Factors are separated by times. Only if something is multiplied onto the entire numerator and denominator can you cancel it top to bottom. Not if it's added or subtracted. You can see, though, that we have our identity on top. We'll have 1 over cosh squared of x, and that's the hyperbolic secant squared of x, or sec squared of x. I don't want to do too much with these since you'll have the joy of discovery of playing with these on your own. You should know, though, that the hyperbolic tangent is related to something called the rapidity function in special relativity. Let's integrate tangent of x dx. The only thing to go on right now is the fact that we're dealing with sinh over cosh. Now we're in the form f prime over f. The derivative of cosh is sinh. So we get immediately the log of the absolute value of the cosh of x plus c. The hyperbolic cosine is related to something called the catenary. The catenary is the line that you get, the curve, when you hang a cord between two poles with free ends. In that case, the shape is like this. It is the shape of a hyperbolic cosine. You should probably know a little bit about the shapes of these curves. It's e to the x plus e to the minus x over 2 for cosh, which means that you have exponential growth and exponential decay kind of added together and averaged. That means the graph is going to look like this. It's even, which means it's symmetric about the y-axis. Whatever you get at x, you get the same thing at negative x because the negative goes away. Sinh, on the other hand, is e to the x minus e to the minus x over 2. And if you subtract those graphs, you get something that looks like this, going through the origin at a 45-degree angle. Tangent, on the other hand, has a very interesting graph. As x goes to infinity, the second terms in both numerator and denominator drop out, and the whole thing tends to 1. As x goes to minus infinity, it's the terms that drop out, and the whole thing goes to minus 1. This curve is interesting in that it has two distinct horizontal asymptotes. A function may have 0 horizontal asymptotes, 1 horizontal asymptote, or 2, because there is a right and a left. You can get different horizontal asymptotes on each side. You don't have to. You could get the same asymptote on each side, or no asymptotes at all. But tangent gives you two distinct horizontal asymptotes. Rational functions never do that. They either give you 0 or 1. This is similar to the graph of inverse tangent. Inverse tangent tends to pi over 2 on the right and negative pi over 2 on the left, and looks very similar to this.